There again. We're on Chapter 7.3, Bonding in Metals. This is a pretty short chapter. There's a few key concepts we want to really learn in this chapter. And a couple things I'll talk about, but very quickly, and I'll tell you what you really need to know on this chapter section. Okay, we're going to talk about the properties of metals, which are very important. You can see that this is a wrought iron railing system, which is found in many cities. You'll especially see these in places like New Orleans and Savannah, Georgia. And it is made out of iron that just has a little bit of carbon in it. It's very tough. It's malleable, meaning that we can hammer it and shape it. It's ductile, so you can pull it into wires. It's resistant to corrosion. And it melts at very high temperatures. So for it to melt here, it would have to get much hotter than the world's ever gotten. Well, with global warming, who knows what's going to happen, but I don't think it'll be that hot. Maybe on Venus it would melt. Okay, so one of the things is, what is the model of these valence electrons? We know the metals, the atoms themselves are neutral, but the valence electrons, are in the outer energy level. What are they doing? When you get a big chunk of metal, that's a bunch of atoms of metals. Let's just think about that for a second. If we think about metals, what do we make wires out of? Copper, right? That's pure copper. So we know that electricity is a flow of electrons. So somehow the electrons are moving through that copper. How are they doing it? Okay, so what we say is the electrons are free to move around the central nucleus by just moving around like a sea of electrons. They're keeping the charge neutral, but they're not staying all the time in the sphere of that specific nucleus. They're moving from nucleus to nucleus. All right, so they're free to move. So that's why we call it a sea of electrons. Okay, so the metallic bonds are the forces of attractions between the free-floating valence electrons and the positively charged metal ions. So what's happening, since these electrons are free to move all over the place, so if I have this as my centers, so the electrons are just kind of like, they're moving wherever they want to go. All right, they're still staying nearby, but they're all moving around. So this movement, these electrons are all moving. That's one electron that I'm tracing. Think of all the other electrons that are going around at the same time. Well, they keep on moving around, so they're attracted to these nucleus, but not just one, so that makes them stick together. Okay? That's kind of what it's like. Okay, we know they're good conductors of electricity because the electrons, it doesn't matter, whose electrons they're using. Electrons can be from anywhere. They're easy to move around, no problem. Okay? So if some enter at the beginning of a bar of metal, the same number leave. It may be the ones that were there already before, but they replace the ones that are leaving with the new current, and when the current stops, the amount that was there originally stays there. Okay, ductility, again, means that you can take a force and push it through what we call a die and make it into a thinner wire. That's ductility. And malleable means you can hammer and press into shapes. I think I talked about like golden domes. Okay, they have what's called gold leaf on them that someone hammered really, really thin and they place on the dome. It's not a pure gold dome. It's actually leaf. In fact, if it was pure gold, it would be too heavy and probably would fall. So what happens is, when you put pressure on it, the cations can move by each other because they've got that sea of electrons. So what we're doing is we're just moving those nuclei into thinner and thinner amounts, and the electrons are moving then into a thinner and thinner three-dimensional pattern. If we did it to an anion, or basically an ionic compound, it would basically move the positive ions closer together, and that would repel it. Okay, the anions aren't moving around, so it will shatter. Okay, whereas since the metals are surrounded by all these electrons, they move freely to balance out the charge. Okay, they're similar because they have 3D crystal-like shapes, and they're dissimilar because metals can be hammered. Metals can conduct electricity in a solid state. Okay. Metals are also ductile. Ionic crystals, we showed, can fracture under pressure. Okay, so what is the crystalline structure of metals? If we think of spheres, we want to get them as close together. Okay, this example of oranges shows how they're kind of put together in what's called a hexagonal close-packed arrangement. We see the hexagon with the 6 atoms or oranges on the outside and 1 in the center. You can also have what's called a body center cubic, where you have a nice cube with 1 in the center like that between the 8 of them. So things like sodium, potassium, iron, chromium, and tungsten have this kind of body center cubic pattern. Gold, okay, the silver and copper, which we call the coinage metals, as well as aluminum and lead, will have this face-centered cubic model, which if you kind of look at it, it's kind of a cube with on each side of the cube, it has like if you think of it as a dice, there's 1 atom there, okay? And so if you think of it as kind of like, I don't know if you ever played jacks as a kid, but each of those balls on the center one is like put inside the cube. Okay, so that's face-centered cubic arrangement. So it has 12 neighbors. Now these are all types of things that we're not going to go into any detail about crystalline structures. Just be aware that they can be put together in different ways. All right. Here's zinc. Zinc is even more complex. It has that hexagonal packing on top and bottom and like a triangle in the middle. This is called hexagonal close packed arrangement. Okay, which of the following models can describe the valence electrons of metals? I would say the best that describes the electrons is D, a sea of electrons. Okay, alloys. Alloys are a mixture of metals. Okay, we talked of solutions are like salt and water, but an alloy are 2 metals that form a solution, so we call them alloys. Okay, for instance, brass is copper and zinc. And why they become important is when we mix them, sometimes their properties are much better than when you have the element alone. Okay, sterling silver. Silver is a very, very soft metal. So usually they put something else in it to make it stronger, such as copper. And so that makes the silver a much more durable piece of jewelry or tableware because we've added another metal to it, made an alloy out of it, rather than having soft silver, which would bend every time we try to cut something with silverware. All right. One of the most important alloys are steels, which can be different percentages of things depending on the type of application they want to use it for. We can see that steel is mostly iron, which doesn't surprise us, but also has chromium, carbon, and nickel in it, and they can have other substances in it to make them strong. Okay, some alloys replace and fill holes in the crystal, so some of the elements will move into spaces because they might be smaller than the rest of it. Others will, just form a new type of crystal. Okay, when they fit inside these spaces, it's called interstitial alloys. Okay, again, alloys are important because they get superior properties, and one application is steel. Okay? And here's some summary information. Make sure you put these in your notes. And our big idea is bonding interactions. Metals are made up of closely packed cations surrounded by a sea of electrons. The sea of electrons model explains why metals are good conductors of electric current and why they are ductile and malleable. That's it, folks.